Kia ora koutou katoa. The ice sheets in Greenland and Antarctica are the largest sources of long-term higher-end sea level rise on Earth today, and the ice sheet in West Antarctica is the largest source of uncertainty in the sea level rise projection. Now, to look at a map of the Antarctic, you might not think that that's the case. The ice sheet in the east is much larger than the ice sheet in the west. The coastline of the East Antarctic ice sheet along the Southern Ocean is much longer than the coastline of the West Antarctic. So to understand why glaciologists like myself are so concerned about what happens next in West Antarctica, we've got to peel back the surface and look at the system in more detail. This is a map of the surface elevation of the ice sheet. The warmer colors are higher, the cooler colors are lower. If you think about that shape, the East Antarctic ice sheet is kind of flat in the middle. It gets steep on the edges. It flows slowly in the middle. It flows fast on the edges. The West Antarctic ice sheet is fundamentally different than that. Rather than a concave down shape, it has a concave up shape. And if we look at what happens in the interior, the ice sheet is high, and as we go towards the coast, it gets very flat. And it's flat because that ice is floating. So there's something different going on in West Antarctica, and what I want to do is talk with you about why that's the case and why it's so important. If we peel back the surface and look at the thickness of the ice around the Antarctic, again, warmer colors are thicker ice, cooler colors in this map are thinner ice, we see that the ice sheet has overrun everything that's there. It's filled in the valleys, and those are the thick places. It's overrun mountaintops, and those are the thinner places. Before there was an ice sheet in Antarctica, there was a continent. And underneath the East Antarctic ice sheet, it's like the continental crust that we find in North America or Northern Europe. But underneath the West Antarctic ice sheet, before there was an ice sheet, there was an ocean. And the ice, as it grew, glaciers and ice caps high in the mountains slowly flowed down toward the sea. They displaced the ocean water, and they covered over the sea floor. And so today, the base of the ice sheet is way below sea level, and that fundamentally creates different flow and different behavior for the ice sheet. To explain this or to understand it, we're going to need a little bit of physics. We'll talk about that physics using a cartoon, and then we'll look at the real system. So this is sort of a slice through the West Antarctic ice sheet. It's thick in the interior, it's thin on the edge. Snow falls on the surface, it densifies, it becomes glacier ice. As that ice gets thick and has some surface slope, it starts to flow. It flows down toward the coast, it speeds up and gets thinner as it goes. Eventually, it gets thin enough to go afloat on the ocean surface. And at that point, we don't call it an ice sheet anymore, we call it an ice shelf. And the boundary between those two, or the transition between the grounded ice sheet and the floating ice shelf, we call the grounding line. And if we want to understand change in West Antarctica, we need to understand what's happening with that grounding line. It's the place where ice that has been stored in the ice sheet returns to the sea. So when we snow on the surface, we're taking water out of the ocean, and sea level might go down. When the ice flows back through the grounding line into the floating ice shelf, the water is returning to the sea. If we do more of that than we do of snowfall, then sea level will go back up. To understand where the grounding line is, we need to understand something about the physics of the system. So we've got gravity is the force that causes the ice to flow. It flows under its own weight. And then a bunch of other forces in the system that balance that gravitational, we call it a driving force. And if we just start in the interior and we think about what the ice has got to flow over, there's some kind of bed underneath the ice sheet, right, the land surface. And the ice has to push over that land surface to make its way to the sea. If you think of a deck of cards sitting on a table and you push sort of down and across that deck of cards, the table resists that motion, and it resists it the most where the cards are close to the table and the least where the cards are far away from the table. And you get some shear in that deck of cards. The same thing happens in the ice in the Antarctic ice sheet. As the ice gets toward the coast, the material underneath the ice changes. So if you imagine now, rather than your table and a deck of cards, you've got some water in between the cards and the table. That water will help the cards as a whole stack shift across the table. And you'll start to transition from a place where shearing is the most important thing to where the whole stack is sliding together. And when we go afloat on the ocean surface, the water is really weak compared to the ice, and there's no shearing at all. It's all just stretching out. And in each of those transitions, the ice flows faster than it did before. So this is sort of at the heart of understanding how the West Antarctic ice sheet behaves. It's going to be the balance of all those forces together that place the grounding line wherever it happens to be. Now, what we worry about in West Antarctica is that if we can do something to change the forces on the floating side of the ice shelf, the grounded part of the ice sheet will respond as well. And I'll explain this in a sequence of steps. If we increase the melting underneath the floating ice because the ocean is warming up, because the atmosphere is warming up, we can cause a little bit of ice right at the grounding line to go afloat. When it goes afloat, it doesn't feel as much resistance as it did before, so it flows faster than it did before. When it starts to flow faster, it stretches more, it thins. When the ice at the grounding line thins, more ice goes afloat. It feels a different traction on the underside. It starts to stretch more, it thins more, the grounding line retreats. When the grounding line retreats, more ice goes afloat. It starts to stretch faster, it thins some, more ice goes afloat. And if we can push the system fast enough, we can actually generate kind of a runaway retreat in the system where the amount of the push doesn't matter anymore, and all that's going on is that internal physics. And the grounding line retreats simply because the grounding line is retreating. We call this a marine ice sheet retreat. In physics, we'd call it an instability. So what we want to know when we study the West Antarctic ice sheet is we understand these physics. Theoretically, this is certainly what goes on, but does it happen in the real world as well? We have a couple of ways we can try to answer that question. One, we can look to the geologic record of the past and say, has this happened before? The other thing we can do, if we want to think about the future, is build a computer model that simulates this kind of behavior and ask, is the warming we expect in the future enough to generate that kind of response? So we'll talk about the geologic record first, and we'll compare what's happening today with what's happened in past warm worlds. So in these plots, I'll show you atmospheric CO2 relative to the pre-industrial conditions, so before people started burning fossil carbon, the global mean temperature relative to the pre-industrial condition, and then sea level relative to where we are today. So the most recent warm time is about 125,000 years ago. It's a time called the last interglacial, when there was relatively little ice in the northern hemisphere compared to today. The ice sheets in Greenland and Antarctica were a little bit different than they are today. And at that time, the world was about a degree warmer than the pre-industrial state, and sea level was a few meters higher than it is today. So we know, no matter what happens next in Antarctica, we've got some sea level rise left to do. And that's for two reasons. One, glaciers and the Greenland ice sheet are melting. The other thing is that the ocean water's warming up and it's expanding. If we want to find a time when atmospheric CO2 was as high as it is today, we have to go back 3 million years to a time that geologists call the Pliocene. And in that world, and the global average was several degrees warmer than today, and sea level was anywhere between 6 and many tens of meters, the estimates vary, higher than today. So the geologic record tells us that as we continue to warm the world by increasing atmospheric CO2, the ice sheets are going to continue to respond. What we want to know next is how fast does that happen? What are the sea level rise rates likely to be? To answer that kind of question, we need a computer model. So scientists who are interested in this kind of question use the geologic record to build models that can reproduce all those variations over climate cycles. They drive the model up to the present day and then head off somewhere in the future. Now, we don't know what the future is like yet because it hasn't happened, but we can make estimates. And these estimates that the Intergovernmental Panel on Climate Change uses are called representative concentration pathways, which is a complicated term, but essentially what it means is that we think about what decisions global communities are going to make about fossil fuel burning and then estimate what the atmospheric CO2 concentration will be like for different kinds of policy and consumption scenarios. And I'll show you models that are driven with two different scenarios, one in which we sort of globally get our act together and limit the amount of fossil fuel burning that we do in the future and keep atmospheric CO2 relatively low. And then another scenario that's often called a business as usual scenario, where we just keep doing more or less what we're doing right now. So here's 500 years into the future for that first scenario, the world in which we're very aggressive in our carbon emissions policies and we greatly reduce the emissions. And in this world, not much happens in Antarctica. The ice sheet doesn't change very much. Again, I'm showing you a thickness map of the ice all around the Antarctic. If, on the other hand, we continue on the path we're on right now, 500 years from now, the West Antarctic ice sheet is gone. And we've lost significant parts, the marine parts of the East Antarctic ice sheet as well. And the global mean sea level rise that we get out of Antarctica alone is about 15 meters. That's a dramatic number. It doesn't happen all at once, it happens over time, so we should look at how the sequence of events unfolds. That's what this plot shows you. The black line is that low emission scenario. The red lines are the high emission scenario with two slightly different ways that the ice sheet and the overlying atmosphere interact. The important thing to look at here is that by the middle of the next century, the rate of sea level rise year on year is between 4 and 6 centimeters per year in these simulations. Those are huge numbers. Other modeling groups who use the same kind of approach will generate slightly different rates of change, slightly different timelines for the magnitude of this change, but the end result is always the same. And it doesn't matter too much. If you live in a coastal community, the difference between 3 centimeters per year and 6 centimeters per year of sea level rise is not the thing you're worrying about. Those are huge numbers either way. What I want to talk about next is whether once we step onto that red line, if we're committed, if that's the direction we're going to go, is that sort of a fait accompli, that if we don't act now, is there nothing else we can do? To answer that kind of question, we need to look in more detail at specific parts of the Antarctic ice sheet rather than just thinking of the system as a whole. So I'm going to talk about some work that I'm doing with Scott Weibel and Charles Jackson, in which we start out thinking about the whole ice sheet, then focus in just on West Antarctica, and then focus in more specifically on one glacier in West Antarctica called the Thwaites Glacier. It's a place that is changing right now quite rapidly. This is a map of ice flow all around the Antarctic, and the warm colors are fast flow, the cool colors are slower flow. You can see there's sort of a network of tributaries that feed into the Thwaites Glacier as it makes its way to the sea. And when we set up this model, what we do is simulate the present day situation. So we create a model that represents this flow exactly, and that kind of embodies the geology as we know it and the climate as we know it in the system. This is a map of the bed elevation underneath the ice sheet, and as advertised, you can see that it gets deeper. The seafloor gets deeper as we go into the interior. The cool colors here, the light blue through the magenta, are elevations below sea level. The warm colors, green and above, are elevations above sea level. So you can see the bed gets deeper and deeper and deeper as we go into the interior. And that runaway effect, if we can get it to start, would indeed continue in this system. So I'll show you two different simulations. Remember, our goal is to try to find thresholds in the system and understand how vulnerable is the West Antarctic ice sheet to this marine kind of runaway retreat effect. So we'll do two things. We'll take our model that's built to represent today quite well, and we'll start to slowly push it, as slowly as we possibly can. Now, what does global warming do? It increases the atmospheric temperature. That increases the ocean temperature. Increasing the ocean temperature generates more melting underneath the floating ice. So the way that we will invoke this change is by doing melting on the floating side of the ice sheet. And of course, you know now from our discussion of the physics that when we start to melt on the underside of the ice shelf, that the grounding line will retreat. And what we're looking for is not the melt-induced retreat. We're looking for the time when the grounding line keeps retreating, even if we turn the melting off. That's when we've actually generated a real instability and a real runaway situation in the ice sheet. So we'll slowly, slowly, slowly drive toward the future. When we find that moment when the retreat rate no longer depends on what the climate is doing, we'll shut off the melting and we'll watch what happens next. Then we'll go back to that time and we'll keep pushing a little bit more, and then we'll turn it off. And we'll compare those two scenarios in a set of slices through the ice sheet that look just like my cartoon slices, except now we have the real shape of the seafloor underneath and the real shape of the ice sheet on top. So here's the state for the slightly shorter, slightly smaller warming and the slightly longer, slightly larger melting underneath the ice shelf. If we go 20 years into the future, indeed, we see both grounding lines are retreating. So we have, in fact, crossed this threshold into a runaway retreat kind of scenario. If we keep going forward in time, however, we see that the scenario that we pushed a little bit harder is retreating faster than the one that we gave a more gentle push. If we keep going into the future, the simulations will continue to diverge. And so what this tells us is that there's always an opportunity to change the pathway that we're on. The larger the push, the larger the response. But any time that we stop, we then lock in that rate of retreat. Right? So the retreat is inevitable once we've crossed this threshold. We're going to get massive change in West Antarctica no matter what we do. But we can limit how fast that happens. Right? We can, through our own choices that we make as global communities, say, we can tolerate some amount. And the sooner we decide to do that, the sooner we decide to limit the warming, the slower this is going to unfold. Now, I've spent all of my career trying to understand what's going on in the systems in West Antarctica. When I first started doing field work in the interior of the West Antarctic ice sheet, we didn't even really know what was underneath the ice sheet. We didn't know how important the subglacial condition was going to be for the rate of flow. Are there questions that we still need to ask? Certainly. Is there more that we need to know? Of course there is. But we know a lot. We understand the basic physics. We understand how to write the equations that describe the way the ice sheet interacts with the ocean and interacts with the atmosphere. We can ask the geologic record really tough questions and get meaningful answers. We can ask these models to show us different pathways into the future, and we can have confidence that the models are showing us, indeed, what the future holds. What we can't do is pick which of those futures is the right one. That's a decision that all of us collectively all around the world have to make together. It's like we're sitting at the top of a hill in a car with our kids, well, with everybody's kids. And maybe we've been pushed over the edge. We're not really sure. Maybe we haven't. But we know, one way or another, the sooner we put on the brakes, the gentler the crash at the bottom of the hill is going to be. Now, maybe we're still up at the top and we can put on the brakes right now and nothing dramatic will happen in West Antarctica as well. Maybe we've already passed that threshold, but certainly the sooner we put on the brakes, the gentler the impact down at the end. Thank you.